Hi, my name is Tom and you are at level 14 out of 30 easy steps to understand everything about Einstein's special relativity. This is the first super level on our mountain. If you watched episode number 1, in which I introduced all the levels, I told you there will be 2 super levels. Number 14, this one, and number 23. So, welcome to the first super level. We will have a major breakthrough. I mean, it will blow your mind. It blew everyone's mind back then, and it still blows my mind. Level number 14, where we discover electromagnetic waves. You want to know? Of course you do. GP, hit it! Maxwell's equations. We have spent level 1 all the way up to 10 to get to level number 11, where it all came together in Maxwell's equations. I strongly recommend that you watch that level, of course, but if you didn't, here we will have a short recap of Maxwell's equations. Number 1. If you have an electric charge, plus or minus, it radiates some mysterious electric field. If it's plus, it radiates outwards, and if it's negative, then the field lines of the electric vector field are coming in. Here they are. Law number 2. If you take a magnet and you cut it in half, you end up with 2 small magnets. You can't separate the North Pole and the South Pole of a magnet. Law number 3. If you have a changing magnetic field, you will get a curly electric field. We had, not just as level 11, we had separate levels for most of these, especially Faraday. Number 4 tells us 2 things. If you have a metal wire and electrons are running through the wire, it will create a curly magnetic field around the wire. And the second thing, thanks to Maxwell's addition, he says if you have a changing electric field, you will also get a curly magnetic field. And these are Maxwell's equations. And in math, they look like this. And, well, basically we spent 10 levels to understand this math, to be able to read these equations. But now you see it in words, in visuals, and in math. These are Maxwell's equations. And now, why is this a super level? There is a major secret hidden within these equations. You want to know the secret, right? I wanted to know the secret. The hidden secret. We do it in words, yeah? Before we, well, let's do it in words. So, again, the 4 laws. A cause and an effect. You have a charge, you get an electric field. You have a magnet, you get a magnetic field. You change the magnetic field, you get a curly electric field. You run electricity through a wire, you get curly magnetism. You change the electric field, you get a curly magnetic field. Cause and effect. So let's imagine we have this metal wire with these free running electrons, and we make these electrons go up and down. What do Maxwell's equations tell us what happens? Well, first, the first law says, well, we have charges, right? Electrons. And electrons produce electric fields. So we have each electron has its own electric field, and because the electron is going up and down, its electric field goes up and down with it, right? That's the effect. 2, we know from the first part of the fourth equation of Maxwell that this current through the wire will also produce a curly magnetic field. 4 was about steady current. In this case the current is going up and down, but still you get curly magnetic field. And because the electrons are not in a steady current, this magnetic field will not be constant. It will move up and down. Law number 3 tells us, well, if we have a curly magnetic field because of 4a, so the effect of the second effect now goes into the cause of the third line, we get curly electric field in response. And that effect can be a cause, and that cause is a curvy electric magnetic field. So here you see cause and effect. Let's see if you can do what Maxwell did. Do you see the secret? Look at it. Especially the last 2 lines. What's going on there? We have a magnetic field creating an electric field and an electric field creating a magnetic field. It's like yin and yang. We have causes and effects that are circular. This is it. The big secret inside Maxwell's equations. And well, as you see in previous levels, I can't put words into the magic and the effect of this. But let's see. Let's look at it. So, in 1865, Maxwell published a paper in which he describes this phenomena. He took his equations. He made several assumptions, like let's look what happens in free space or in vacuum with the electric and magnetic fields. Let's say there are no currents in the space around the metal wire where the electrons go up and down, and do a whole bunch of math. And what came out of it? I made an animation. I'm really proud of it, but you can be the judge about this animation. But here it is. You see a metal wire on the left. It's vertical. Inside are green electrons. And I opened up the wire a little bit so you can see that they are actually there. And they're going up and down. We have a frame of reference, an x-axis, the y direction and the z direction. In this case, we are interested in the white x direction. And what we see is that we have in blue the electric vector field. And because the electrons are moving, this vector field is also changing through time. And in red, we see a magnetic field. And if you look at it, my eyes just follow the wave. We get a wave. We get what they call an electromagnetic wave, EM. There it stops, so we can focus a little bit more on the image. So it's very, very, I would say, I always go follow the wave. But what you should do is go back in the movie and try not to follow the wave, but stick to a single point on the white line. Because that's just a fixed location in space, and see what happens at that location. And you see that at that specific location you have an electric field that grows in strength, diminishes, changes direction, etc. So at that single point the electric field strength does this, and perpendicular to it the magnetic field does this. So if you were in that location, you're not traveling with the wave, you're in this location, and you would be a charge. A charge is being pulled by the electric field. So you want to go up, oh, I want to go down, oh, I want to go up, I want to go down. If you would be a magnet in that location, oh, I want to go left, oh, I want to go right, oh, I want to go left. So that's what happens if you are stuck in a location. From the equations, we can tell that the strength of the electric field E is not the same as the strength of the magnetic field B. there is a constant between them. And the constant is 1 divided by the square root of, and you should be familiar with all these things, the magnetic constant multiplied by the electric constant. How about the velocity of this electromagnetic wave in the x direction? Maxwell equations also gave that one, and it's the same as the constant between the electric field and the magnetic field. 1 divided by the square root of the magnetic constant, which is just a number, multiplied by the electric constant, which is just a number. So this velocity is, well, just a number, and you can calculate it on your calculator. Awesome, right? Let's see. Oh no, I'm not the only one who found this very awesome. Let's see what others told us. So Einstein, he said, this is the most profound and the most fruitful that physics has experienced since Newton. That's a big compliment coming from Einstein, right? Because Newton, he is the greatest, right? He is the greatest of all. And he says, Maxwell, you did something which is the most mind-blowing stuff ever since Newton. So Feynman, also a well-known physicist, he said this is the most significant event for mankind in the 19th century. In fact, he told us, if you can see in previous levels, if you would go 10,000 years into the future and look back on the 19th century and you ask someone then, what is the most significant thing that happened in those 100 years? They will tell you Maxwell's equations and the discovery of the electromagnetic wave. Go figure. A lot of stuff happened in the 19th century, right? Carl Sagan says it differently. He says, this discovery has made more impact on human history than any 10 presidents. And I told you in previous levels when we talked about Maxwell's equations, without them we wouldn't have radio, television, remote controls, internet, Wi-Fi, cell phones, radar, microwaves, etc., etc. Everything that runs on a battery or power is possible because of Maxwell's equations, and everything that goes through the air, like radio, is possible because of the discovery of the electromagnetic wave. So there you go. Super level stuff. It's decision time. You are good to go to the next level. I'm okay with it. You are okay with it. Everyone's okay with it. But, of course, if you are brave and you want to know more about this super discovery, we will deep dive a little bit more. It's up to you. Okay. You are curious, which is really good. Let's see. I mean, this story is so great. It's about Heinrich Rudolf Hertz. We all know Hertz, because it tells us something about the frequency of something. How many hertz is it? And he is among the greatest scientists at number 73. And, when Maxwell did his math on paper, it was just math on paper. How can we put this to reality? So Hertz actually started to put a metal wire and making the electrons going up and down and see if something happened. And yes, he proved the existence of electromagnetic waves. So it was not theoretical anymore. It was really there. Let me see. In some papers he showed that they could jump. He was able to make an electromagnetic wave travel over some distance, and that it also had a speed, a velocity. So he said, he's right. Maxwell is right. He called him Maestro Maxwell. But he also said, it's of no use whatsoever. We cannot see these things with the naked eye. They are there, but it has no applications, I guess. I mean, this is so fun. I mean, these are really brilliant people. They discover something completely new, electromagnetic waves, and they say, well, I don't see the point of it, oh, great, but, I don't see any applications. Well, we know its applications, right? It's all around us, in everyday life, in every second. So, later, Marconi, he made a machine, an apparatus, to make electromagnetic waves go from A to B over a long distance. And in the 1900, Fessenden, he sent audio across 1.6 kilometers. You have to imagine, this is a time where we don't have cell phones or internet, cars or whatsoever. I'm not sure if they had cars, but I mean, if you want to get a message across, you would actually have to write it down with a pen on a piece of paper, go on a horse, go ride and give the paper or tell someone. I mean, that's the way communication was. And here it is. We could, well, I'm not sure if that's true. Maybe the telephone was there as well. I'm not sure. But, you can imagine sending information, in this case, audio information, through the air was completely new. We could not do this before. And here it happened. So, 6 years later, Christmas Eve, Fessenden makes his first public radio broadcast, and people can listen to the radio. So, and the rest, as they say, is history. You can still now escape to the next level, but if you are like me, you're like, this is so awesome, I want to know more. Let's do rock climbing. It will be rock climbing, this will be the point where you might say, oh, no, I shouldn't have done this. Just, just watch it and be entertained, I would say, because we are going to do heavy math. We're going to do the most heavy math on Einstein's mountain right now, because this is what I wanted to do. I wanted to actually do the mathematical mumbo jumbo and go from the 4 equations of Maxwell to the electromagnetic wave equation. Want to see how that went? Let's go. We start with equation number 3, which says the curl, the nabla and the cross product, remember level 7, if the curl of an electric field is proportional to the change of the magnetic field in time, with time. There it is, the partial derivative with the crooked deltas. If you watch previous levels, we discussed all these bits and pieces. So let's start with this one. Yeah, let's do this. Hold on to your seat. Boom! We take the curl of equation number 3. I asked myself, why would you do the curl of the curl? I don't know. Maybe because you can, and they did. So if you take the curl of the curl, you put in the curl of the change of the magnetic field with respect to time. Then we shuffle, we rearrange. We can take the partial derivative outside and we can take the curl operator inside the brackets. Then we see, we see the curl of the magnetic field, B. Wait a minute, we had an equation for the curl of the magnetic field. That was equation number 4. Let's put equation number 4 in there. There it is. And then we say we're not interested in the wave going through some medium which is fully charged. We want to have free space. No currents there. So there are no currents. So J, the current density, remember, that is set to 0, and we end up with a constant multiplied by the second derivative of the electric field with respect to time. That was the curl of the electric field. Cool. Next, we can calculate the curl of the curl in a different way. We did this. It was also rock climbing, right? In level 7, I did the full derivation of the curl of the curl. And in the end, the evil mathematicians, if you saw levels, Mathematicians are evil. They summarize the end result with secret symbols, making it totally unreadable with a gradient and a dyadic product and the vector Laplacian, etc., etc. I don't like that, just give me what you're doing. Give me the partial derivatives. Give me what you are doing. So in level 7, you can find in the rock climbing section exactly what this means. If you zoom in, if you open the secret symbol, the triangle, and you know exactly what to do. And then it's not complex. It's a huge equation, but it's not difficult anymore. This is a small equation, which is totally unreadable and therefore unusable, for me at least. But that's me. But let's apply this way of calculating the curl of the curl. Here it is. The curl of the curl. We just apply the equation from level 7. And because charge density is constant, charge density was even 0, I think. That means that the divergence of the electric field outside of the metal wire is 0. The divergence is the nabla with the dot product. So we can take away the first part of that equation and we are left with the vector Laplacian of the electric field with the minus sign. So we calculated the curl of the curl twice, so the end results should match, right? These two should be the same. We can shuffle a little bit when these two are the same and then we get this equation. The second derivative with respect to time of the electric field is some constant multiplied by the vector Laplacian of the electric field. And now, if you have a very good memory, level number 12, where we talked about waves and wave detectors, we also met Leonhard Euler, the second greatest scientist ever lived and the greatest mathematician ever lived. So, you could argue that maybe he is bigger than Newton, but, I think Newton is the greatest and many, many others do as well. He made a wave detector. He told us that if this equation holds true for a random vector field, the second derivative of the vector field with respect to time is some constant times the vector Laplacian of that vector field, you have a three-dimensional wave. It's a wave. And now let's look at the end result, what we just did. Yes, so the electric field is a wave. We have found the wave equation for the electric field, which were the blue vectors going up and down when we looked at the animation. Let's speed up. We do the same for the magnetic field. You can just follow. Fill in the curl of the magnetic field, B, which is number 4. And if we say charge density is 0, then, no, it's current density, that's why. J is current density, and charge density is rho. And, in previous levels we discussed this. I made an error, I apologize. It's some constant, right? So we take the curl of the curl again. I'm not going through the entire equation. It's almost the same as we did with the electric field. And then we apply the curl of the curl in a different way. The end result should match. We shuffle, and again, we see that the magnetic field is also a three-dimensional wave equation. Et voila! Hidden within Maxwell's equations are two waves, a magnetic field wave and an electric field wave. And together, they are called an electromagnetic wave. And here we see it again in full glory, because I just love this animation. And, well, I also spent a lot of hours on it, but here it is. And try not to follow the wave. Just try to fix a point on the white line and see what happens if you were a charge or a magnet on that white line. And we know some of the wave equations we see there. We see that the strength of the electric field E and the magnetic field B is just a constant in between them, and that the velocity of this wave is that similar constant. The electromagnetic wave. I think this is it, right? Yeah, this is it. Oh. So we have to close. I want to thank you for watching this level. I hope you found it a super level as I did. And see you next time on the next level. GP, hit it.